I like to think the iteration method was invented by someone just sort of drawing random lines and noticing patterns, and this is the thought process that might have happened in the history of maths. Well, we've rearranged our equation to, instead of saying f of x equals 0, so where does something cross the x-axis, instead of looking for those, we've rearranged it to say x equals g of x. So now we're saying, where does the graph of some other function g, where does it cross the line y equals x? So it's the same answers but phrased in a different way. X equals, where does the line y equals x cross this thing here? And you can see it with a red dot on the picture here. Now, if we take a value of x here and we feed it in to g of x, okay, we get that fascinating. We get this height here. How is that helpful? Well, what if we just do this? Dun, 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 dun. Oh, look what's happening! Ta-da! Okay, so by doing that little thing I just did, we managed to get ourselves onto the root. So if I can just work out what on earth I was doing other than singing a little song and going in a spiral, if I can work out what I was doing mathematically, then I can use that to hone in on the root. So what did I do? I picked a random value of x, x0, and then I put it into the g function, the thing that was on the other side when I made it say x equals. So I worked out what g of x0 is. Okay, then what did I do? So that got me to this height here. Now what's this process going across here and then down there? What on earth is that? Normally ending up here is because we've put something, this value, into g, isn't it? So if I was down here and I put that into g, I would get that height there. So that's normally what that is. I might draw that on in green so that we can see what I'm talking about. Ending up here is usually because I put this here, this value of x, into the g function, the pink one, and got that height there coming out. That's how I would end up here. So how do I get from there to there? Well, I seem to be doing it by going via this green line. What is this green line? It's the line y equals x. And what I got out here when I did x0, g of x0, was a y value. Y equals g of x0. We usually use y for an output and x for an input. Now, by going across to this line here, I'm taking my y value and I'm turning it into an x value. I'm sort of reflecting it down onto the x-axis. So my y value is becoming an x value using this line as a reflector. Now once I get that, so my y becomes an x, let's call it x1 instead of a little scribble. Now what do I do with that x1? I take that x1 and I feed it into g. Okay, so I do g of x1 and I call that y. Here it is, y. Now I want that y to become an x. So instead of going all the way across to that y, bouncing back down to the x, and then I feed that back in, and then I get a y, which I change into an x, which I then feed back in. Okay, let's go through this slowly and highlight the corners as we get there. So we start with our x. We feed it in here, and we get a y. Then we take that y, we bounce it down onto the x-axis. So this is bouncing down, and we bounce it down onto the x-axis, and that gets us a new y when we feed that new x into the function g. Then what do? We go to the y-axis, we use the line y equals x to bounce it down to being a new x, x2. So g of x1 is a y value, which we then convert into being an x value. So this is now here. We do g of our x2 and get out a y value. We do g of our x2 and we get out a y value. So the black dots are the y values. And then we use the line y equals x to get that y value. and make it into an x value. Down it comes. So this is x3. And then we feed that x3 into the g function and we get out a y. There it is. And then g of x3 is a new y value, which we then use the graph of y equals x to change that y into an x. And then we do g of that x and we end up here. So we do x4, g of x4 is y, which is going to turn into an x, which is then going to get put back in, which is then going to produce another x once I've used that graph to reflect it. So this one here, that's a y value, but by going across to the line y equals x, I make it into an x value, which I can then put into the g function, and then using that y, I can bounce across to the line y equals x to produce an x. I put that x into the g function, and so on and so on and so on, and what I keep getting is x's which are closer and closer and closer to the true root, and that's why it's working. Here's a better picture, done slightly more nicely. I'm starting quite far away from the root now. I start with a random x, I feed it into g, I use x is y to make that into a x which I feed in. Then I use the line y equals x to turn my y 0.7 into an x is 0.7, which I then feed in. Then I go and once I've got my x, then I find out what the function is doing. Then I use the line y equals x to produce an x. Then I find out what the function is doing. I get a y. Oh dear, look what's happening now. I'm going away. I came in. Oh, came in. Really close. But now look. I'm going away. Oh no! Away I go. Away, away, away. So this one isn't working at all. And now I'm spinning round and round there, so I'm not getting closer. So it's not just this line y equals x that's important. It's also your starting value that's important. And it's also the way you've rearranged your equation. Because this way of rearranging the equation, x equals this curve, is not producing an iteration. It looked like it was, but no. Now I'm going outwards and outwards and outwards. Now in Edexcel, they're going to tell you how to rearrange your function. So you will get x equals a function, and they'll tell you a start point, and that start point and that function will converge inwards. But if it doesn't, then maybe they'll say show that this one doesn't converge. This is basically what's happening. It's just that the exact choice of that right hand side of that thing that we're comparing to y equals x isn't going to work. I'll show you some other ones that do and don't work. These are the 4 things that can happen. So monotonic, don't worry about what the words mean. Convergence means getting closer, and divergence means not getting closer. And, well, I can explain it, it's not difficult. Monotonic is where this happens. We go to the line, then we go y equals x, and then we go to the curve to find out what y is, then we change it to an x curve, change it to an x curve, change it to an x, and you can see that the x0, the x1, the x2, like this, they're getting closer and closer, like that, towards the true root. Oscillating convergence is where you bounce around. So we start here, that's our x0, then we go to the curve, then we change it into change the y into an x, that gives us this one. Then we go to the curve, then we change the y into an x by going across here, that gives us this one. And you can see now that even though I am converging in terms of what's happening along the x-axis, I'm bouncing from side to side, x0, x1, x2, x3, x4, x5, x6, x7, like that. Bounce, 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 bounce. In, but oscillating either side of the true root, whereas this one goes down, down, down slowly to the true root. Now, this is where we've rearranged the function into x equals this curve or x equals this curve. What if we rearrange it into x equals this curve here? What happens? Well, we kick off, we start, we choose our x0, and in fact we can start really close to the root with this one. Let's start here with our x0 really close, and we go in and we're hoping that we're going to get even closer, but no, We don't. We get pulled away. So we change it into an x, we put that in, we change it into an x, we put that in, we change it into an x, and you can see that we're just going further and further and further out, and we are never going to come back. That is sad. That's diverging. This one's also diverging, this fourth example. So we start, again, we can start really close to our root. Let's start in here, this is our start point. We go up to our g, change it into an x, find out what the y is, change it into an x, find out what the y is, change it into an x, find out what the y is, change it into an x, and you can see that I'm spinning out of control. And the x's that we get, it oscillate further and further away. There was my start point. Then I had x2, x3, x4, x5, x6, x7 like this. I'm getting further and further away, oscillating either side of the root. So it is really important that when we have a function equaling naught and we're trying to find out where it crosses the x-axis, if we can't find that and we want to use an iteration method and we rearrange it to say x equals something, and now we're asking where does the graph y equals x cross some other graph, and it'll be the same answer, but we can use our iteration to find it. It is really important what this function is, because if it ends up being like this or like this relative to the x graph, x equals y, then your iteration process won't work, it'll diverge. What you need is this or this, and it's all to do with the gradient of the function at this point here. That's what controls it. If the gradient of your g function is between 0 and 1, or between -1 and 0, then you're going to be okay. If the gradient of your g function at the point you're interested in, at the crossing point, if that's smaller than -1 or bigger than 1, then you're going to get this divergence, either monotonic, going off to infinity, or spiralling out of control. You don't need to know that. It's just for the sake of interest if you're wondering what's going on. For the purpose of the exam, all you're going to have to do is stick a number back in and back in and back in to a particular function. Whatever comes out, put it back in. Whatever comes out, put it back in. Do it 4 times, get an approximation to the root. Nice, easy exam question.